All right, everybody, welcome back. We've made it to Chapter 10. We didn't define it this way before, but we talked about an acid-base reaction focusing on the H+, where the H+ is going. So this is technically the Bronsted-Lowry definition. We didn't use that term before. But if I focus on where the H+ is going, H has left that, and H has ended up over there. Well, this gives us a definition. We say an acid donates H+. Well then, conversely, bases accept H+. HF is an acid. It donated H+ to the base, which was NH3. NH3 is a base. It's accepting it from the acid, which is HF. Okay, we've been sort of saying that, but now we've got it more formally defined, Bronsted-Lowry. So we can say acids are proton donors. And by the way, I'm saying H+ or proton interchangeably. We talked about that in Chapter 5. But if that doesn't make sense, you might want to stop and think, well, what really is a hydrogen atom? What really is an H+? Well, then bases are proton acceptors. And if a proton is that, what kind of thing would we expect a base to be? Professor Paula Abdul said opposites attract. So I would suspect bases might include something that's negative, maybe something that's partially negative, or maybe simply a pair of electrons. Negative, 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 all of those are going to attract an H+. Okay, so then this is trivial, but let's make a quick table. Acid, base, in each of these reactions. Stop the video, sort that out real quick. It's trivial. All right, you sorted it out, right? You stopped the video, so we're going to focus on the H. And what I have to do is say, well, what happened over here? And by the way, here is a typo. That should just be Br minus. So this loses its H, H2O becomes H3O plus. So let's see, the acid, HBr, I'll do it all the way down, HCl, NH4 plus. Again, I'm looking from left to right, reactant to product side, who lost an H plus? The base, H2O in that case, the base, HCO3, bicarbonate, hydrogen carbonate. And here the base is that. And again, all we're looking for is at H plus going like that. Okay. Now again, review. We talked about acid-base neutralization reactions. And again, I say, okay, well, H. And we talked about a very specific case where hydroxide is the base. Now, I'm not going to write everything in there, but I'm going to say, well, in general, H comes off an acid and hydroxide off of the base. Now, you'll notice there's still some leftover parts. You go, well, there's still some ions like sodium, magnesium, potassium, fluoride, nitrate, phosphate. Well, what do we do with those leftover ions? Leftover ions. Well, there's our ionic compound. Okay, take those leftover cations, anions, put them together into an ionic compound, and we get water. So we'd say acid base, sometimes we say acid base, an ionic compound, and water. When it's an acid and hydroxide is what the base is. Now, it got a little messier, but more interesting, I think. Here I've got an acid. And I have some variation of carbonate for my base. Bicarbonate, carbonate, carbonate. There's some very similar things going on over here. Ionic compound, but I end up with this when I sort of put the H plus on the base. Well, so what have we got here? We've really got, well, let's do this one. What I've got is H plus going to the carbonate. Well, carbonate's -2, so I need H2CO3. 2, 1, 1. What are the leftover ions? Well, there's sodium and there's iodide, 2 NaI. So H, carbonate, I get this H2CO3. Now, here's a funny thing about this, and I talked about this right before spring break, right before everything got crazy. This is very unstable. It immediately decomposes into water. And, oh, now I've got an ionic compound and water. What's left over after you take H2O out of there? CO2. There's the fizzing. So, we could say it like this. Again, H plus some variation of carbonate, bicarbonate, carbonate, whatever. We get the leftover ions. Gives me an ionic compound. And if I put 2 of those on there, I get H2CO3. But the part I have to memorize is, oh yeah, H2CO3 always decomposes into water and CO2 gas. So there you get the fizzing. Okay, well, just to remind us, what if I have H plus HCO3 minus? Well, I still get an ionic compound. And I get H2O and CO2. And really all I did was say, well, H plus is going to stick on something negative. Now, here's something new. If I think about all these nitrogen, if I were to draw this, I'd have some variation of this. Over here I've got H plus, H plus, H plus. Well, guess what? The H plus is going to stick there. And I see it right here. Oh, there's an extra H plus. There's an extra H plus. There's an extra H plus. So this last definition is just, if I have an acid plus a neutral compound with nitrogen, I end up with, so I'll draw this like this, H plus. I end up with H, N, 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 and a plus charge there. So, acid-base neutralization, hydrogen hydroxide, acid plus carbonate, I get water and fizzing. And now I have this, acid plus something with protons, like nitrogen. I end up with an N plus there. Okay. Let's come back to this definition again. We said, oh yeah, that's what we saw before. Acid, base. But what if we think about this reaction? There always is a reverse reaction. Almost always. There's some reverse reaction. So now if I think, well, wait a minute. What if I think about this reaction going backwards? And I look over here going backwards. There's where my H plus is going. So now I've got, oh wait, fluoride is a proton acceptor. So it's a base. Going the other direction, NH plus is a donor. So it's an acid. So all I've done is say, well, okay, let's not forget about the reverse reaction. Well, the H plus goes the opposite direction, and everybody sort of flips places in some sense. Well, what about this? Chapter 7, we say, well, what's at equilibrium? Well, going from left to right, we've got that. Now, what if we think about for the reverse reaction? And the term we're going to use is the conjugate base and conjugate acid. There's multiple ways to think about this, but one way to think about it is, well, what about going in the reverse reaction? Well, in the reverse reaction, the base, I'm going to do them blue, and my conjugate acid, NH4+. So we have to have terms thinking, well, wait, are you talking about the forward reaction, acid and base, or the reverse reaction? And then what's the relationship here? How do I turn an acid into a conjugate base? How do I turn a base into a conjugate acid? Well, let's say conjugate base. It's the base for the reverse reaction. Conjugate acid is simply the acid for the reverse reaction. Now there's another way to think about it. How did I convert this acid into a conjugate base? I just removed H+. So a conjugate base is an acid minus 1 H+. A conjugate acid over here, well, it's the base with just base plus 1 H+. And we'll use those two terms. We'll think about the reverse reaction, or we'll think, oh no, you turned an acid into a conjugate base. You turned a base into a conjugate acid. And we look at 10.4. We've got some practice for this. Looking for the H+, 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 H+. So I've got Cn minus plus H3O plus, Cl minus plus H3O plus, Cl minus, NH4 plus, 2NO2 minus, rather than do the net ionic, let's do the whole thing. So I'm going to strike that, and I'm going to write MgNO2 plus 2 waters. H is going to the hydroxide there. Okay. Now, without even having a reaction, we can talk about the conjugate base. It equals the acid minus 1 H+. So conjugate base, Cl minus. Go down that list and fill those out. Stop the video and fill those out. You stopped it, right? You're coming back, and you put Cn minus, HCO3 minus. I didn't take both, I only took one. H3PO4, H2PO4 minus. Here we know that extra H is on that nitrogen, CH3NH2. Conjugate acid is a base plus 1 H plus HClO3. Finish those up, then restart the video. You did it, right? H2PO4 minus, HPO4 2 minus, CH3, and I have to remember that nitrogen has those electrons, and H3 plus. Okay, a little more practice. Page 10.5. let's skip this one. What's likely to be a Bronsted-Lowry base? Well, I'm looking for this, or this, or that. So when I look over here, that certainly looks like a candidate for to be a base. Ag+, nope, that's not going to accept an H+. Fluoride, sure. Bicarbonate, sure. These are the same things we just did on that other page. Now the answers in your book, 10.3, the answers in your book there for this one as well, 10.1, it might make sense to do those. If this makes total sense to you, ignore them. If you want a little more practice, the answers are there, and the answers to that one are in the back of your book. Let's look at page 10.6, which really is a review of what we've already done. Hydroxide, let me do that in blue. Hydroxide, hydroxide, acid. HCl plus AlOH3. And I'm really thinking of this as, okay, that's hydroxide. That's H+. Okay, I'm for sure going to get water. And what are the leftover ions? Well, I'm going to have a chloride and aluminum, AlCl3. Now I could balance this thing, but what you might start to notice is, well, I've got 3 hydroxides here. I'm probably going to make 3 waters. If I'm going to make 3 waters, I need 3 of the HCl's. And that ends up being 1 and 1. You could work out the magnesium hydroxide. The answer's in the back of the book, but that might be a good idea. Do the magnesium hydroxide there. Here, neutralization means all the acid and base is quote-unquote used up. There's no acid or base left. So I look here, that must be base and a base. There's my H+, H+. So I might say, well, why don't I just go ahead and do this, this. And I can see, well, I've got 2 H+'s there. That's -1. I'm going to need 2 of those. This is -2. Each of those is +1. I might do that. Now, I don't have to do it that way, but as you start to see, well, what's really going on, you'll probably find it easier to balance. So let's see. So I would have, I'm going to write H2CO3, 2 of those, plus the leftovers. Now there's not much left over here. I've used up all of that. I've used that. So the only sort of leftover, SO4 2-. That's perfectly fine. Now I have to remember, this thing doesn't stay together. I go, oh, wait a minute. This thing turns into 2 waters and 2 CO2. Similarly here, I go, okay, I've got H2CO3 plus. The only leftover I've got is nitrate. And I think, oh, wait a minute, that's not stable. That's going to break down into H2O plus CO2. Similarly here, H+, ammonia, looks like that. I've got 2 H's, so I'm probably going to need 2 of those. Stop the video and complete that thing. You stopped it, right? So you said, okay, I've got 2 NH4 plus SO4 2-. Now this last one, 10.23, very similar. Now here they're saying, hey, you're going to make an ionic compound. So sounds a little scary, but let's see what we've got. We got C2H5 NH2 plus HCl. And I think, well, this is H plus, and there's nitrogen, like that. And I think, okay, well, that's pretty straightforward. That's going to go there. So I might just say C2H5NH3 plus. And what's left over, Cl minus. Oh, if somebody said make an ionic compound, well, I've got a cation and an anion. I could write C2H5NH3 Cl. Okay, hopefully mostly review. We've seen acids and bases exchanging H plus before. We have a little variation. We've seen that before. We have this, which is a little bit new. But again, it's H plus trying to find something negative. All right, the next idea is we're going to do some stoichiometry with acids and bases, and we're going to use the concentration to sort of figure out moles and volumes and things like that. So I will see you next on page 10.7. Hang in there.